Good afternoon, everyone. So it's my pleasure to welcome Professor Armin Schikorra. So he is a distinguished professor working in PDE, geometric analysis, harmonic analysis, and calculus of variations. He is a professor at the University of Pittsburgh, USA, where he is also serves as the director of the graduate studies. He did his PhD in 2010 from RWTH Aachen University, and NSF Career Award, Humboldt Research Fellowship are among his many recognitions he received throughout his career. And it's my pleasure to welcome Professor Armin. And today, this week, he will be telling us about the topological obstructions for Sobolev maps.
Thank you for having me. Thanks to the organizers for inviting me. All right. Yes, I want to talk. I know this is a conference called, or a school called Geometric PDE. There will be essentially 0 PDEs, but I want to claim that this is about PDEs because I will talk about function spaces and how topology kind of does something to our Sobolev spaces and what topological effects maybe we can see and not see. And this is important when you try to do calculus variations or stuff of this sort. When you minimize things, you kind of want to understand the topology. And I think it's a very cute subject, like very cute effects that we can see, and maybe some of them are surprising. I do have typed notes. There are a lot of typos in those notes, but those are the notes that I'm actually now using. So if you want to see them, I will keep updating them and try to remove some of the typos as I find them. This is the link. So tinyurl.com and then 53EUY7VT. And, you know, it's a PDF file. And, you know, if you cannot read my handwriting, this might be a way to follow. All right, so I want to talk a little bit about topology, but it's really, really baby topology, okay? So I want to start, and please interrupt me at any point when you don't understand what I'm saying, maybe. So I want to start with defining the degree. And now all I'm doing is essentially the one-dimensional degree, because that's for the effects we're going to see and talk about enough, and it's easy to draw, okay? So just so we are all on board, I kind of assume that everybody knows this. Let's look at a map. F going from the one sphere to the one sphere. Okay? And I want to recall, just so we are all on the same page, and what we're doing today is pretty basic, the mapping degree. Okay? So I will kind of interchangeably use the degree of F, or in 1D, we call it the winding number. Okay? So this is the domain, this is the target, and the degree counts how many times the domain gets wound around the target. So that's a little bit difficult to draw. So it's easier to draw the target, which is a one-dimensional sphere, as like a fattened up, you know, kind of a fat sphere. Okay, so this is S1. Just for drawing purposes, I draw it as an annulus, but it's one-dimensional. Okay, and let's draw a sample map. So everything is continuous. We're talking about smooth for all we care. So what is a map like this? It starts somewhere, goes around, maybe twice, then it comes back, does something like this. You can also add a little bit, something like that. Okay, so this is the map. We fix some orientation here, let's say this one, and then we just follow. Okay, now I have to redraw this map, and then this map. Okay, so this is the picture of the map, F going from the S1 to S1. All right. Now, in order to compute the degree, again, this is the winding number, it's very simple, is we pick our favorite point, maybe the North Pole, and we stand here. Okay? Now, that's a point, right? A point in this flattened picture is a line. So this is the North Pole. We stand here and we simply count how many times does this guy go through that point. and we take into account the direction. If it's counterclockwise, no, clockwise, we count it as a +1. Counterclockwise, it's a -1. So in this case, it's not with many colors. This is clockwise, so we count it as a +1. This is clockwise, this is +1. This is anti-clockwise, counterclockwise, it's a -1. We sum this up, and so the degree is +1, +1, -1. So the turning number is 1, which tells us this particular map winds around the target once. Okay? Now, definition kind of clear, right? Or known. Okay, now a few pathological cases or things we have to take into account. These are continuous maps. How do we count things which only touch this point? So, for example, if I make this tiny little bit more, something like this, right? So we have a strand that just touches, goes back, and then goes through. That counts as a 0, as a +1 and a -1 immediately. Okay, so this here is a +0. Okay, that's maybe clear. Just let me see that I don't overlook anything. If we never see the line, that could also happen. There's no reason to be subjective. That's a 0 as well, right? So not touching this green line is a 0. Touching, we said. And now, of course, we also can have the situation that we go infinitely many times through that line, right? That this could be a problem because we have pluses and minuses. But if we go infinitely many times through this line, only finitely many times of those times we come not right back, right? Because this is a continuous map, so it's absolutely, it's uniformly continuous. So most of the times when we go through, we will come back right away. It costs somehow energy or distance to go completely around the curve. So even if we have infinitely many crossings of this line, most of the times you can count them as a +1 and immediately a -1 again, which is a 0, okay? So for any continuous map, the winding number is that thing, that number, and it's well defined. That's what I want to say, okay? Good, we all know that, of course. Few properties, again, just to be on the same page. Does it matter where we stand? No, of course not, because it's a homotopy invariant. So this winding number, whatever the map is, this number doesn't change if we stand here or there. How do we prove it? By picture, right? This is essentially homotopy, but we can just move this slowly. And when anything changes, maybe at this point, right, here we have 3, 3, 3, 3 strands, and then suddenly we have only 1 strand left. What happens? We have to go through a touching point, which is a ±1. Right? So with this picture proof, we kind of say, as we move continuously from the North Pole to the West Pole, you know, this number will stay constant. Okay? So nothing changes if this is just an arbitrary choice and it's not relevant. A few more things. Okay, for now I will refer to the winding number. So if f of x is constant, then the degree of f is 0. It's also trivial because we either don't see it or it's a touching point. And the other thing that I need is if f of x is the identity, then we go exactly around once here, then the winding number is 1. Okay? That's pretty much all the topology we're going to talk about. Okay? This, I mean, if you're familiar with homotopy groups, I will write things in higher dimensions. If you're not familiar, just think about this. There's no real difference for our purposes. Now, the last and very important property of the degree or the winding number is the homotopy invariance, right? That's kind of the main point, that this is a topological quantity. All right. Again, I assume we all know the statement, but I just write it here. If F and G go from S1 to S1, I always assume continuity. I'm not going to write it. If they are homotopic, then the degree of F is the degree of G. All right, what does homotopic mean? Homotopic means I take this picture and I just move strands and stuff continuously, right? So as I move, for example, this orange part towards the left, again, just before when we move this person, the number doesn't change. Analytically, a homotopy, I prefer always, let me write, oops. They are homotopic if, well, there exists a homotopy, which is a continuous transition from one map into the other, meaning there exists a map, call it H, which goes from 0, 1, domain into target. So this I like to think of as the time. This is how the curve changes at time t. And so again, this is continuous. H of 0 is F. H of 1 at time 0, we are the curve F. At time 1, we are the curve G. Okay, that's a homotopy, everything continuous. Again, the picture is just that these strands move over time and we never are allowed to rip anything apart. Okay, and then again from the picture, I hope it's clear, and we're not going to prove this stuff. We have homotopy invariance, the degree doesn't see this, right? That's really the main property of degree as an object. All right. Good. Two reformulations that we're going to use a few times, or two versions of what we're trying to do in Sobolev spaces. So let me first, I call this a corollary out of homotopy invariance. So here the homotopy is kind of on the 0, 1 cross S1, right? So we can think of this as a cylinder. But we can also think of this as a ball, because at 2 points, well, we can think of this as a ball if one of the two maps is constant. So a corollary that I want us just to have in mind is if F going from S1 to S1 is the trace or the boundary of a map capital F going from B2 to S1. So if F going from the sphere to the sphere can be extended into a map from the ball to the sphere, again continuous, then this necessarily means that the degree of F is 0. Okay, again, I assume this is kind of clear. Why is this clear? Well, if F is essentially the boundary of this map from ball B2 to S1, this map from B2 is a homotopy. We simply say, proof, H of t comma x is F of t x, right? At t equals 1, this is the original map little f. At t equals 0, this is a constant map, and that proves that the degree is 0, okay? I'm writing all these things because we have to redo them in Sobolev spaces. All right, now, that's one way to say this. The other way to say this is like a more obstructionist point of view. Okay, so this says if we have a function between the spheres which can be extended, then the degree is 0. The other way to say this, if the degree is not 0, then it doesn't exist an extension, right? So there's an obstruction to extensions. Again, I want to write this down just for the purpose of thinking about the same statements in Sobolev spaces. So if degree of f is not trivial, then there exists no map. Let me write this again. We go from S1 to S1. There exists no map B2 to S1, also continuous, such that f on the boundary is little f. Okay? Now, all these statements are trivial, I hope, right? But it's just 2 points of view. So this is something like non-existence of extensions, right? So there's a topological obstruction to extend this little f into the interior, or the more classical homotopy invariance. All right. Any questions? All right. Good. So why do we care about the degree? I guess there are many reasons, but one of the undergrad reasons we may have learned is something like the fixed point theorem by Brouwer, right? So again, something I assume we all know. May we have our favorite proof of it. I write it in n dimensions just for fun. So here's the fixed point theorem of Brouwer. We go from the ball to the ball. I assume those balls are all closed, right? I don't want to write the dash. Okay, so we have the closed unit ball in n dimensions. We go into n dimensions, and it's continuous. Brouwer. Then there exists a fixed point. X bar in Bn such that f of x bar is x bar. Okay, we all know this. Okay? And it's one of these beautiful theorems that has like 20 or 100, I don't know, many different proofs, right? Different ways to prove them. And I want to go through the proof. I mean, you all know the proof, but again, just for later use. One way to prove this is the following. Okay, assume not. Then f of x is never equal to x. Surprise. So then everything is continuous and we are compact on a compact set, right? So this is compact. So there exists an epsilon greater than 0 such that the infimum of x in the ball, f of x minus x, well, it's never 0, since we're in a compact set and everything is continuous. This here is at least this epsilon, which is greater than 0. Okay, that's equivalent. And now we just have an explicit construction of a homotopy of the boundary curve 1, the identity, into a constant. All right. So consider h of tx. So we start with the homotopy and then we look at what we see. And what we're going to look at is this map. I don't specify where x lies because we have to be a bit careful. But so what is this? What kind of map is this? This is certainly a map that goes into the sphere, right? It has norm 1, unless it's not defined. Okay? So let's be a little bit careful. Let's look at the properties. If t equals 1, this is a map x minus f of x divided by x minus f of x, and x minus f of x is never 0, so this is just a map into the sphere. And it doesn't matter whether x is anywhere in the ball. So this guy goes from the ball into the sphere. Right? And this is actually not only true for one, actually we know this, let me write this continuous. Actually we know this for all t suitably close to 1. For all t larger than t naught, this t naught depends on epsilon, right? On this number, if t is suitably close to 1, this number will not be 0, and then this is a map into C. Okay, so this is a number less than 1. So for t very close to 1, this is just a map from the full ball into the sphere. And so from before we know, this is a map at the boundary which has degree 0. Right? So this says that h of t, I just had 1, on the boundary, this degree, this is a map now from the sphere to the sphere, so the degree is defined. And the degree is 1 because it's the, it's 0 because it contracts into a constant. Right? All right. Good, good, good. Now, when t is less than t0, which is less than 1, then maybe x minus t f of x can be 0, and so this is not defined for all x's. But of course, when the norm of x is 1, then x minus t f of x is also not 0 for any t less than t0, which is bounded away from 1, because this here is at most 1, this is strictly less than 1, and this here has norm 1. Okay? And so we have that h tx goes from the boundary to the boundary. It's the continuous. And in particular, h from 0s is a nice continuous map. What's the degree of this guy? Well, since this is a homotopy in T, everything is continuous in T, right? When we stick to the boundary, the degree here was 0, so the degree must be 0. Degree of h 0x on the boundary is 0, but what's this guy? If I didn't screw up the numerology or the formula, where I wrote it, yeah. Right, if t equals 0, it's x over mod x at the boundary, mod x is 1, so this here is the identity. So under the assumption that there's no fixed point, the identity is homotopic to the constant, which is impossible, so we have a contradiction. Right, the degree of the identity is 1. Okay, contradiction, so there must be, well, one fixed point. Also important, of course, it's a topological argument, right? We have no idea how many fixed points there are. It's not the Banner fixed point, which is an analytical argument. It gives us one fixed point. This could have one fixed point, a lot of fixed point. You can prescribe the set of fixed point. There's absolutely zero control, right? These are qualitative results. All right, I hope we all agree, right? This is the Brauer fixed point. That's how you can prove it also in infinite dimensions. And hopefully we agree this is like a kind of, useful result for whatever is our purpose. All right. That's very old stuff, right? Brauer is whatever, before Second World War. Can we do the same in Sobolev spaces? Right, that's the basic question, and I thought the fixed point theorem is like a nice illustration of what we can and cannot do. So let's do, again, just to be all on the same page, talk about Sobolev spaces. I mean, I assume everybody is familiar with Sobolev spaces, just so that we have same notation. Okay, W1P means function is an LP, and the gradient is also an LP distributional gradient. All right, right? When I write, so F is an LP, the N and the distributional gradient is also an LP. All right. Now, I may write now and then W1P Bn, and then here there is a manifold, some subset of Rn. Okay, this is simply the kind of lazy version of saying F is in W1P Bn Rn, and F of x is in the manifold almost everywhere. Okay, nothing worse than that, and we will never touch this H equal W problem in what we do. All right, now, okay, we can look at this somehow in Sobolev spaces. We see that we will have to restrict to the boundary, right? Sometimes we restrict these maps to the boundary, so we have to talk about traces, which we all know. If a function is an LP, of course, it doesn't make sense to evaluate it at the boundary at all, but we have the extension, the continuous extension of the continuous boundary operation, which we call trace. So there exists a map from W. I only care about the ball, so I write the ball into, and then here we see the fractional subspace. This might be important for what we do. So this is the numerology, just to remind everybody. W1P in the interior of some ball, can write larger. Right, the trace, extending the continuous trace, is, the formula is 1 minus 1 over P, right? And this is on the boundary of Bn, which of course is Sn minus 1. And so we have to talk now and then about fractional Sobolev spaces, WSP. On manifolds, but on manifolds it's just Euclidean and you glue that thing together, right? We don't have complicated manifolds. So let's define that. So let's generally have a d-dimensional manifold. Everything is compact and everything is smooth, right? Nothing complicated. Well, the space is defined by its norm, or its semi-norm, what the gradient is, and it's f of x minus f of y. Then we have an s here, which is not 1, so s is between 0 and 1. And so we essentially look at the Hyder coefficient, f of x minus f of y divided by x minus y to the power s, right? That's kind of the Hyder, well, norm. It's not a norm, it's pointwise. Then we take the LP norm of this guy, dx dy over x minus y to the n, and the n should be replaced with a d, right? This is one way to write this. Of course, we need to write the 1 over p, right? And sometimes, of course, we also write this just as f of x minus f of y to the power p, x minus y, and the dimension plus s times derivatives times p dx dy, 1 over p. Okay? So, okay, that's the fractional Sobolev space. So WSP are all the LP functions with this norm finite. Okay? And LP always in the sense of the surface pressure of this thing. All right? Okay, good. And now we all know the embedding theorems, right? I mean, so when we had the talk of Andrea, right, we talked about this L2 star. This is kind of what I want to get at. So just as a reminder, okay, this. So, yeah, I only care about the Mori embedding. So we embed into C0 1 minus n over p, log if omega is weird. If 1 minus n over p is greater than 0, then W1p is actually continuous and embeds into C0 1 minus n over p. The same, of course, and the proof is also exactly the same, is if you put here an S, then we put here an S. And then we put here an S, and it's the same embedding. Now, for our purpose, very important to be careful again. I assume everybody knows this, but just to be careful, of course, this is an LP function. This is not an LP function. This LP functions are a class, right? They have representatives. These are the continuous representatives. There's only one continuous representative of every Sobolev class, but this here is a class of functions which are the same when they're almost everywhere the same, right? And for something like fixed points, this is kind of an important distinction. All right. Now, the interesting case where, things are non-trivial is the case when this is not greater than 0, but this is equal to 0. Okay? Sometimes this is called the conformal case, which is very misleading because nothing is conformally invariant. So if S minus n over p equals 0, then WSP does not embed into C0, it embeds into BMO. Okay? We don't really care about the definition or BMO too much, but just as that we have it once. BMO is simply take f of x minus f of y, take any power you want, I like 1, take the supremum over all balls, and have this thing to be finite. Okay? This is BMO. This is the BMO semi-norm. Okay? You see it has some similarities here. You essentially erase this and replace this by mean values. Okay? So this is F in BMO. Actually, these spaces, and we will use this, don't only embed into BMO, but into VMO. So we can say that as R goes to 0, these norms go to 0. Not only is this finite, but they go to 0 if these radii are small. But we will see. All right, this is the Sobolev spaces. We all know them as well. And now we go back to our fixed point theorem. And since we talk about easy things, erase all this. Okay, so let's try to prove the fixed point theorem for W1P. And let's start with the easy case. If P is larger than the dimension, then everything is continuous and there's nothing to prove. Kind of boring. All right, Brouwer fixed point. So assume that F is in W1 P Bn into Bn, right? Again, that just means that F is less or equal than 1 almost everywhere. Right? If P is larger than the dimension, then there exists a fixed point. Well, this is immediate by the Maury embedding theorem, because P is larger than n. These things have, okay. F itself may not have a fixed point, but its continuous representative will have a fixed point. Right? Okay, that's, all right, P greater than n. All right, next case. What if P is less than n? No, right, completely wrong. What's the example? X over mod x. It's always the example for these things. The hedgehog, right? This is a map going from Bn into Sn minus 1. And if you compute the gradient, all right, it's 1 over, not equal, but it behaves like 1 over x. 1 over x is an LP for any p less than n. Right? This is an LP for any p less than n. At a log, around 0. And so this guy is in W1P. How many fixed points does it have? Infinitely many, so it's not quite there yet. But we make a minus sign, and we have no fixed points. Right? Now you could complain. It's kind of a stupid question to talk about fixed points for functions which are not everywhere defined. Right? So we could say, haha, minus x over mod x, 0. That one has a fixed point. It's kind of stupid though, right? So, okay, so if P is larger than n, we didn't have to deal with this because we just worked with the continuous representative. If P is less than n, we should first discuss the notion of what is a fixed point. All right, now we cannot talk pointwise, right? So we talk kind of measure and density, all right? That's kind of the laziest way. I'm pretty sure there can be a more reasonable way. And let's erase all of this. So we need a new notion of what we could think of as a fixed point, and the notion is just, we assume that where we are close to a fixed point, that always has, you know, some sort of measure. Okay, so this is my definition. So f going from whatever, Bn to Rn has, and I decided to call this is not any official this is not really used anywhere, right? So we just use it for this purpose of this first lecture. So we say it has essentially a fixed point if whenever I look at the set, you see that, don't make a mistake. We look at the points x in Bn so that fx minus x, well, it may, I mean, the equal 0 case is too restrictive. So we just look at the points which are almost fixed. And we say that at every scale, there have to be some. And some means in a measurable sense, so the measure need to be full. Okay? I'm going to refer this as essentially having a fixed point. Because now this is defined for measurable functions. Okay? So we say this, we have essentially a fixed point if for any epsilon greater than 0, the set where we are epsilon close to a fixed point has positive measure. Right? Maybe one can improve this to some capacity version, but I don't really care. All right. Sanity check, if f is continuous, right, and it has a fixed point, then by continuity, right, around the fixed point, this will be, for any epsilon, there will be kind of an open set where this is true, right? So this stays positive, okay? And if f is continuous and this holds for any epsilon, then there's a sequence of points which converge, since we're on compact sets, to a fixed point, right, by continuity. So for continuous maps, if f happens to be continuous, this is the same as having a fixed point. Okay? All right. Now we have a notion of fixed point. Still, this is a counterexample. For W1P, when P is less than n, there's no fixed point. Also in this sense. Because this map clearly maps everything to quite far away. Okay, so there's no fixed point. So P larger than n is boring because it's, you know, continuous. P less than n is trivial. There's nothing to prove. And x over mod x is the counterexample against everything. So the question, and what I want to talk about, is this case when P equals n. So we have not continuous functions. But still, we can try to talk about the existence of something like a fixed point, right? Running a topological argument. And this, I thought, is a cute first kind of illustration of what one can do and then motivate some things. All right. So I rewrite this. So that's a small theorem. Let F be in W1N from the ball to the ball. Then F has essentially a fixed point. Okay, statement clear? Right, again, pointwise doesn't make any sense. We can change everything pointwise, so we may decide on this notion. And okay, so let's prove this. Okay. Now, you could ask, is this a reasonable theorem? I mean, it's true, but is it a useful theorem? I don't really know, right? This is kind of a fun exercise, let's say. All right, where's the proof? There's the proof, right? I mean, it's set up so that kind of the proof is the same thing. We just have to make sure that everything works. So we will use exactly the same homotopy. What do we have to show? Well, first we have to show that everything is correct in this class W1N, right? So we have to kind of talk about that this here is in W1N on the whole ball. Okay, then we have to show that this here is a continuous deformation in W1N. And then we have to say that there is a contradiction of transforming a Sobolev map into a Sobolev map. One has degree in some sense 0, and the other has the degree in some sense 1. Right? And this is where we need topology in Sobolev maps. All right? So, all right. So let's start talking about the proof. So first we do the technicalities and then we define the actual topology. All right, first lemma. Right, we have the proof essentially written down here, we just have to check every item. All right, first things first, we need to discuss this, right? Now, maybe I write this here, so assume not. So what does this mean? There exists an epsilon greater than 0 such that the set f of x minus x less than epsilon has measure 0. Right? All right, claim this guy is in W1N. So let me give this a name. If we do not have essentially a fixed point for any t0 close to 1, we have that x minus tf of x, x minus tf of x is in W1N. I mean, if it's defined, it will be into the sphere. And not only this, right? So t, some t0 to 1. This map is in the sphere, and t maps into this thing. Is a continuous transformation in time of the Sobolev space. Okay, this is we have to prove. Okay, so the proof is pretty easy. We just have to be a bit careful. Well, first attempt at this proof, we know this number is almost everywhere not 0, so we compute the gradient and see what happens. All right, the gradient of x minus t f of x divided by x minus t f of x is equal to, okay, everybody can compute this, but I want to write this in the right form. I wrote it, let's see, in the lazy form. Okay, so we write it like this. So this is the gradient hitting this. Now the gradient hitting this is plus 1 over x minus t f of x squared. Then the interior derivative. And then we have the scalar product. And this is gradient of x minus t of x. All right. This here is almost everywhere greater than epsilon. So this here is an ln. This here, do I have too many of those? Yeah, again, x minus t f of x without the square is greater than epsilon almost everywhere. So this is 1, or this is an L infinity, and this is an LP. So this is in the same space as this guy, which is in Ln. So x minus t f of x divided by x minus t f of x is in W1n. Correct? No. That's not a correct proof. Right? Computing almost everywhere the derivative and hoping that that tells us that we're in a Sobolev space is wrong, morally and mathematically. Okay? Why? Be careful, right? This is the Heaviside function. Compute the derivative almost everywhere at 0. The function is not in the Sobolev space. Right? It's the same as what we do with the fundamental solutions. Okay, not a problem, obviously. Right? Just something to be careful about, right? We have to kind of regularize. We compute, now I will screw it up, right? So we compute the gradient of this, show it's uniformly in LP by that computation, there's no difference. And then as delta goes to 0, since we have a uniform bound, we have weak convergence to a W1P or 1N function by Fatou or whatever you want to call this. And it converges pointwise almost everywhere, so we have proven that without this is in W1N. Okay? But that's kind of, intro analysis. All right, so we assume this has been proven, right? And in the same way, a little bit with the regularization, we see that this here is actually a Lipschitz map, right? We compute the gradient of this guy minus the gradient at some T2, and we see this is bounded by T1 minus T2. So this proves that we're even Lipschitz continuous in time into the Banach space of Sobolev maps, which happen to lie in the sphere. Okay? All right, any questions? All right, so we have that. So this here takes care of this part, right? So we are not continuous, we are just in W1N, the ball into the sphere, and this here is all continuous. So if we can define in the trace sense the degree, then the degree, if we define it correctly, should be 0. Right? Okay, so this is when t, the time is very close to 1, and then we go below 1. Okay, and now we have to restrict to the boundary. So either we have to prove that we're uniformly in this fractional Sobolev space on the boundary. Lazy way, which is proven exactly the same way as over there, is to prove let T0 be less than 1. F in W1N, the ball into the ball. So f of x is less or equal than 1. Then this here, x minus t f of x divided by mod x minus t f of x. I don't want to work with the trace yet, just because it's a lot of integrals. It's easier to prove that this is in W1N. It won't be in W1N on the whole ball, but on the whole ball minus a small annulus, and the annulus is bounded, thought of by this T0. So here I just went a little bit closer. 1. So if we go to the annulus that is between the radius 1 and 1 plus T0 over 2, where this here is T0, this here is in the Sobolev space, exactly by the same argument as before. So for any t between 0 and t0. And this implies, and it's also Lipschitz continuous, and this implies that we are also continuous in the trace, because the trace is a continuous operator. Okay? Good. So how do we prove our beautiful theorem? All right, here it is. We have essentially a fixed point. Assume not. There is some epsilon that this holds. Consider exactly the same thing. This is in W1n. And here we homotope continuously to something which should have degree 1. So all we have to prove, I make a list, is this. Okay. We have to close this argument. Again, we have proven all the easy technicalities. We have to talk about the degree of trace maps. So we need to define the degree for maps F in this case, 1 minus 1 over n, n boundary of Bn to Sn minus 1. Again, think about one sphere if you prefer. So what do we have to do to define the degree? Well, first, we have the continuous degree, right? So somehow this should coincide if F happens to be continuous. So we kind of have to define a notion of a degree for this thing. We have to say it coincides when we are continuous, and then we have to show it homotopes. So let me write this down. So maybe we call this degree tilde. Degree tilde of F is the same as the normal degree of F if F is continuous and in this space. Okay, this is important. So that's an extension. We need that homotopies, which are continuous in time, into the space 1 minus 1 over n, n minus 1, as n minus 1, do not change the degree. So if I have one map F and another map G, and there's a continuous way to transform from one into the other, and continuous means that the Sobolev space norm changes continuously, then they have to have the same degree tilde. Okay? And then, kind of for the finale, we have, okay, then we have shown that our degree tilde here at the level 1 and at level 0 must be the same. At the level 0, it's the continuous map identity. So we know here the degree is 1. So here we still have to show that the degree is 0. Right? So we have to show this extension theorem. So if F is in W1n, Bn, Bn, then we have to show that if we restrict in the sense of traces to a map in W1 minus 1 over n, n, then the degree tilde, please, should be 0. And when I say this, I mean into the sphere. Right? So everything which can be extended into the interior in the Sobolev space we are interested in should have degree 0. Okay? So this is what we have to prove. I mean, we have to define things and we have to prove things. All right. Any questions? Now, the good thing is we don't need to know anything about the degree besides its homotopy invariance to define an extension. So this is maybe surprising. I don't know. This is essentially due to Brzys and Nirenberg from the 90s maybe. I have a more precise reference in the notes. But so this is always possible. Whenever you have a homotopy invariant map on maps between manifolds, then you can extend it to exactly those Sobolev spaces, W1 minus 1 over n comma n. What's so special about them? These are essentially the BMO spaces, right? So if S is 1 minus 1 over n, and n is n, then S is n, then S times P is n minus 1, which is the dimension of the trace, right? So we're exactly in this realm where we are not continuous, we don't gain continuity at the boundary. If we're W1n in the interior, the boundary is not continuous necessarily, but at the boundary, we're still in VMO with respect to the boundary, right? And for those, we can define any homotopy invariant quantity, right? All right. And again, this is Brzez and Nirenberg. And we refer to this as VMO degree because the point about their result is that you can do this for VMO. I didn't really define VMO, but everything can then be put there and our spaces belong there, okay? All right, so here is, I tried to make this in the most abstract way possible. Again, we care maybe about the degree between spheres, but this is an abstract nonsense result. So let's write this as a theorem. So assume we have manifolds, let's call one MD and N in R. And smooth, everything can be extended to, you know, crazier targets or stuff like this. But for our purpose, let's say smooth, compact, manifolds, no boundary, everything can be extended to these situations if need be. Again, think of two spheres, even one sphere if you want. And MD means d-dimensional, right? So we can define the Sobolev space. All right. Assume. Now the degree gives me an integer number. This is not needed, right? The general homotopy groups map into whatever, right? So we don't need integer numbers. So, okay, take anything. For my sake, let it be a subset of R. It's completely irrelevant, right? Any set really works. Assume we have some subset and we have some notion, which I will call degree, right? Goes from X to Y, where X are the smooth or continuous, I wrote continuous, we can say smooth. So consider the space of smooth map. Take any map that maps that thing into whatever space you want, and whatever set you want, really, with the property that it's homotopy invariance. Okay? With property if F and G are homotopic, that's well defined, right? We take a map from M to N, from M to N, G goes from M to N, and there's a homotopy transforming this into this, that's homotopic. Then this degree, that's why I call it this way, doesn't change. That's the only property we really need, okay? So no local constantness or anything like this. So assume we have something with, when we are homotopic, the degree stays the same. Again, think of the winding number. Okay, these are all the assumptions. Then, and again, you can do this in VMO, which I don't want to define and talk about. So for us, let's go from 0 to 1. And let's call, okay, I want to rule out W11. So let's say that D over S is not 1. And let's look at the Sobolev space, which is this critical Sobolev space, Ws d over s. D is the domain dimension into the manifold N. Okay, again, this just means these are maps defined on this manifold in the Sobolev class, mapping into Euclidean surrounding space that almost everywhere are in N. Okay, then there exists an extension, we call it degree tilde, from xs tilde into y, such that they coincide on the intersection space. So the degree of f is the degree of f if x is continuous and in this space. Okay, so it's an extension. And degree tilde is continuous with respect to topology. What we really care about is degree tilde has the following property. For any f in ws, for any s in xs tilde, there exists an epsilon, and it's kind of interesting that this epsilon depends on f itself, greater than 0, such that for any g in xs tilde, such that g minus f is less than epsilon, we have that the degree is constant. All right, so what does it say? This says whenever we have a map F, around this map there exists a small neighborhood with respect to the space Ws d over s, a small neighborhood where all other g's are getting the same degree, right? They have the same value. The reason will be that they're homotopic, and hence, since this is homotopy invariant, as we have to show, they are the same. Okay? Now, such a statement in particular implies that this degree tilde stays the same as we follow homotopies. Because when we follow a homotopy, we move in time between maps that are very close to each other, so this stays constant. Okay, so this implies that we are homotopic with respect to the constant with respect to homotopy. Again, this here is this embedding into VMO, right? This number where the Sobolev exponent is infinity, but we don't embed into continuous functions. That's again the interesting case. Again, the same statement is wrong if this P, the integrability, is less than that number. Counterexample is x over mod x in some form or shape, right? And it's trivial, this whole stuff, if this number is larger than d over s, because then we are continuous. In continuous function, we can just modify their smooths. Okay, so this is kind of the only interesting case. Now, there's a third thing, and I run out of space and I'm too lazy to write it, right? It's also this degree is independent of the s. So if you have two s, s1 and s2, and they are somewhere between 0 and 1, and you have a map which is both in xs and xs tilde, then the degree is the same. So it doesn't, this degree doesn't see the s because it's actually defined on the VMO map. Okay? So this extension is s independent in some shape. Okay? So statement is, once we have anything homotopy invariant, we can extend it to these critical Sobolev spaces. Clearly not below, again, x over mod x, some form or shape would be the counterexample. Above this Sobolev exponent, trivial. But the point of this result is we can extend it into this VMO case. Okay? Now that we have to prove. That will take us some time. Okay. So let's start discussing the proof of this. Now, again, I want to stress that this dependency makes a lot of problems in applications, right? And this is different to the continuous homotopy theory, okay? And this is kind of the first step to prove anything in this direction, is to look at the continuous case and prove some easy theorems. So at the very end of all this, we will get back to this essential fixed point theorem. But let's first look at statements about manifolds. At least we go to geometry from topology. All right, first lemma, which I'm not going to prove, because it takes too long, is if we have a compact manifold in a surrounding space, that's a compact manifold in a two-dimensional plane, there exists a small neighborhood, for the sphere it's actually quite bigger, where I can project back into the manifold. So there exists a map from a slightly fatter space back into the manifold. Okay? This is, I mean, nearest point projection is a stronger argument even, but so the statement is, let n be any compact manifold. So without boundary. Then there exists some radius, call it delta, because we could think of it as very small, such that, and a map, pi going from a neighborhood of this manifold back into the manifold, and pi on the manifold is simply the identity. And this is smooth. Okay? Right? This map, unless this is topologically very trivial situation, or generally very trivial situation, doesn't exist globally. You cannot project all of R2 back into this manifold without creating singularities, right? But close to the manifold, this always must exist, and you kind of see at some point these in the sphere case, right? The origin has to be taken out. That's the only point. Okay. I don't really care for our purpose that this is the nearest point projection. This is somehow orthogonal or anything like this. This is not relevant for us. So, although I call it here, right, this will not be important. Now, this delta is a purely geometric constant. How do we prove it? Implicit function theorem, right? Around every point, we kind of go into the orthogonal space, right? And we, by implicit function theorem, we see that we, foliate kind of the neighborhood, and then we take a covering because it's compact space, and we get a one-to-one relation. That's this thing, right? Essentially, we project back in the normal plane, and that's somehow the proof. All right, this is very important for basic homotopy, because as a corollary, this proves this very cute statement. All right. Let's have a compact manifold without boundary. Everything is super smooth. Then there exists a number, and this number is uniform. I mean, not uniform, but it just depends on n, such that whenever two functions, two maps into this manifold are closed, they're homotopic. So for any f g, I chose here to go from m into n. So we have two maps f and g. They go into this manifold M. And we know that f minus g is uniformly less than delta. Then f and g are homotopic. Okay? So two maps that are uniformly closed pointwise, right? So they're uniformly closed, are necessarily homotopic, right? Proof is a one-liner, but I want to compare this to this statement, which is different. So here we say in the Sobolev space, two maps which are close are not necessarily homotopic in a slightly different way, right? So for each F, there exists a small neighborhood so that every G that's close to F in that neighborhood is homotopic to F, yes. But this epsilon depends heavily on F, and we will see why. Whereas this here, and this is extremely important, doesn't depend, this is a completely geometric constant. Doesn't depend at all on how F looks or G looks. Okay? This is a very crucial point that we will use and we don't have for WSP. I have until half or until half? Okay, all right. Okay, I promise this is a one-line proof. Let me write down the homotopy. All right, we need to find a homotopy. And here it is, T f of x plus 1 minus T g of x. Ta-da. All right, if T equals 1, this is F. If T equals 0, this is G. And this is super smooth. Only one problem, it doesn't map into the manifold. How do we make it map into the manifold? Well, the distance, htx, well, is the distance, say, to F. The manifold is less than htx minus f of x. And this here is less than delta times 1 minus t, right? And so this is small. So all we have to do is we have to project this back into manifold. This is a smooth projection because we stay close to the manifold. This is smooth, and this is a homotopy. Okay? The proofs for the Sobolev space will be a little bit more fun, okay? But this is, okay, important. We have a uniform constant, and now we kind of have to move everything to Sobolev spaces. How are we going to define this? Very simple idea. This is how we'll end. The degree of f is simply the limit. Look at modifications. Okay, it's kind of obvious. Mollify f as a map between manifolds. Take the limit as epsilon goes to 0, hope it converges. And then prove all the properties. All right, and this we do the next time. All right, I end here.
Is such an extension unique?
Say again?
Is such an extension unique? Is it known or?
Yes, I mean, it's unique. I mean, we will prove that it's unique by this approximation. I mean, yeah, I mean, there's, yeah, trying to think about a situation where it would not be unique, but it's essentially unique. It's essentially a density argument, right? So what we are proving is by this modification that somehow we have a density situation, even though we don't really have continuous maps.
You also mentioned that the degree may not be.
Sorry, I'm essentially deaf currently, so I have to do this.
And so you mentioned that the degree may not be integer. So in this definition, is there an example where the degree is not integer?
Define degree.
I mean, so I mean, as you mentioned, for continuous, it is the same as the usual one.
Yeah. So if you call it degree, it should be an integer, right? Yeah. But I kind of, everything that you look at here, you could think about general homotopy group. And homotopy groups may be Z2 or Z plus Z2, right? So you have these weird, where you only have 1 and 0 as a number or stuff like this, right? So this also works for those. If you want to call that a degree, people will frown most likely, but you can call that a degree. It's a map which is homotopy invariant, and then Y would be Z2. It still works.